This is exercise 11D, looking at integration by parts, which is an attempt to integrate things which look like products, a bit like the product rule in differentiation, but it doesn't always work quite in such a simplistic way. For a start, sometimes you integrate products using integration by substitution that we've seen already, but other times we use the method of integration by parts. So let's have a look at it. This way is going to bring up what's called a late rule. First of all, let's look at the form of the rule itself. This is the formula for integration by parts. It's given to us. It's in the formula booklet. And you'll notice it's saying integrate something, u, times by something else, which we call dv by dx with respect to x. And this is the formula we use. So that implies that one of these has to be a u, and the other one is this thing that we're calling dv by dx, which is a bit weird. When we did the product rule, one was u, one was v, and this is a bit more complicated. To determine which one is which, we use this late rule. And the late rule comes about from the type of things we're trying to integrate. So if we've got a logarithmic expression, that's an L, some algebraic polynomial, like a 2x or a 5x called cubed or something like this, that's algebra. The T stands for trigonometric expressions and the E for exponential expressions. And the U, the thing that we're going to call the U in our formula, is the thing that's highest up the list. So logarithms would always be the U, whereas exponentials will always be the dv by dx. So bearing that in mind, this late rule, you can see the 2x is like an algebraic thing, and the sin x is obviously a trig thing. And so using this, the algebra is at the higher of the two things, and therefore my u is going to be the 2x. And my dv by dx, my other thing, is going to be the sin x. Now, I don't write that straight away. I'm going to write u and v there. I'm going to write du by dx here, and dv by dx here. And dv by dx is the other one, this sin x. So you notice the way I've done this, these are on opposite of the sides of the diagonal. The differential of u is 2, because 2x becomes 2. And this one I have to integrate. And of course you should remember that sine cos minus sine minus cos. If I go from this to this, I have to integrate the sine, and that becomes minus cos of x. So now I've got this, the integral of 2x sine x. Now some people quite like to write, rather than writing all that again, they just write I equals, capital I for the integral. So you get into that habit, that becomes a useful habit later on. So I'm writing I equals this thing, and the formula says uv. So I look at this and I go, well, it's 2x times minus cos x. So I'm going to write that as minus 2x cos x. And it says then minus the integral of v du by dx. V is minus cos x again. Now I could write minus cos x here, but it says minus, so minus and minus is a plus, so it doesn't always work out like that, but this time it does. Cos x du by dx was 2. Alright, so I can chuck a 2 in there as well, and because it's just a number on its own, there's no x's, I can chuck it at the front. dx. So, minus 2x cos x. Now this is the only integration I've got to do then. I've got to integrate cos, and integrate cos becomes, go upwards, goes to sine. So plus 2 sin x. And don't forget your constant. So my capital I equals that. That's what I reckon anyway. So it says minus 2x cos x plus 2 sin x plus c. Yes, it works. So that's my first example of integration by parts. Here's my second example. I've got x and e to the 2x. Well, I've already said exponentials are always the dv by dx. So u equals x, that's the algebraic one. And my dv by dx is going to be the other one. So I did say I was going to write v at the top, and then du by dx here, and then dv by dx here. That's a v. So this is my e to the 2x. Now let's differentiate this one. Differentiate x, you get 1. Integrate this one, you get a half e to to the 2x. Hopefully you've remembered that rule when you integrate e to the 2x's. So I chuck this in, my I is this lot, is now it's uv x, that. So it's a half x. Notice you slide the x in between usually, minus the integral of, this is v du by dx, which is this diagonal. So, oh, and it's times by 1, so I can ignore the 1, so it's just be a half e to the 2x. I'm going to integrate that again, dx. And so this becomes a half x e to the 2x. 2 goes on the bottom, becomes minus a quarter e to the 2x plus a constant. And I could probably take out something as a common factor there. I didn't. So that's the answer I've got down there as well. Now this is a definite integral. Now definite integral because it's got limits. So just bear that in mind. I've got an algebraic thing again, I've got an exponential thing again. So again, using my late rule, the algebraic thing is higher than the exponential. U equals x. Du by dx equals 1. V equals dv by dx equals e to the x. So that's the, oh, and if I integrate e to the x, I get e to the x. This is quite a nice example actually. So I'm going to say this is I. So therefore my integral is the is uv. Now uv x e to the x minus the integral of v du by dx. That's just e to the x dx. But this is great because the answer to this is x e to the x. If I integrate e to the x, I get e to the x. Doesn't change, but don't forget this is actually got limits, and it says limits are 0 to 1. So 0 to 1 it goes in. If I put 1 in, I get 1 e to the 1. Notice that, minus an e to the 1 is e again. So e to the 1, I can just ignore the 1, just write e, and you often see that. Minus, I'll put 0 in, 0 e to the 0 minus e to the 0. Now e, take away e effectively here, this is 0 minus, now 0 times by anything is 0, so this is really, this is easy to think it's 0, actually it's 1, anything to the 0 is 1, so that's minus a minus 1. I think the answer is 1. And it is 1. Third example, x to the 5. So this time I've got, this is an algebraic thing, but this is a log thing. So this is unusual where the algebraic thing isn't the u. So my u will be the log x du by dx v dv by dx. So this is x to the 5. So this one I differentiate. If you differentiate log, you get 1 over. If you integrate x to the 5, add the power, divide by the power. And it's because you end up with this algebraic thing here when you differentiate log, that's the reason we do it. So set this equal to I, therefore the integral. That just saves you having to write it all out. Sometimes it's quite painful writing it all out. So it becomes uv again, no uv. So it's x to the 6 over 6, we tend to write that first, log x, minus v du by dx. That's what the formula says, integrated, so the integral of v du by dx. And notice this becomes x to the 6 over 6 log x. And this kind of cancels, it becomes x to the 5 over 6. Now, the formula said add a power, I integrate, divide by the power. It's already over 6, divide by another 6 is 36. That would be the answer, apart from this definite integration again. And my limits are 1 and 2. So let's chuck these numbers in. So if I chuck the 2 in, I get 2 to the 6. Now 2 to the 6 is 64. So this is 64 over 6 log 2. Put the 2 in, again, I get 64 over 36. And then I have to subtract. I have to do exactly the same thing, but I put 1 in this time. So 1/6 log 1 minus 1 to the 6th is still 1 over 36. So I think this becomes 63. No. It's log 1 is 0. Oh, that's handy. Let's just check that one. I haven't done a stupid mistake there. So log of 1 is 0. Good, yeah, I didn't make a stupid mistake. And 64 over 6 is the same as 32 over 3. So 32 over 3 log 2, they're the only logarithms I've got. And I've got minus 64. Effectively, minus and minus is a plus. So if I add on, I think I get minus 63 over 36. And what is 63 divided by 36? It's 7 over 4. So I think it's 32 over 3 log 2 minus 7 over 4. And that's the answer. And so this is our first look then at integration by parts. So we are going to, in class, do a few practice questions on this. So I hope you're ready for those. Once we've done those, we'll then have another look at some of the harder examples, because this, I should warn you, is just like the first glance at this. I think we've got 3 lessons in total on integration by parts. So best of luck.